in the Stoppel lab, we're really interested in developing new materials for applications in healthcare, as well as other sustainable materials. And in order to do that, we really wanted to focus on finding a platform for production of natural materials that's native to the US. So what you can see here is a Plodia interpunctella. This is an Indian meal moth, or the pantry moth. It's native to the US and is actually the #1 stored grain pest here in the US. So in our work, though, we're not just interested in leveraging the silk fibers produced by the organism. We're also interested in using this organism as a silk fiber bioreactor. And so to do this, we are able to genetically modify these little organisms and alter the structure of the proteins produced. So if you think about the very hungry caterpillar, the first line of the book is in the light of the moon, a little egg lays on a leaf. And it is at that stage that we do the genetic modification using a micromanipulator and a glass pipette and introduce our genetic modification components at the egg stage. Then these eggs hatch into our little caterpillars, and our caterpillars go around and produce this modified silk protein. So this modified silk protein can then be collected and turned into a wide variety of different materials. Our favorite one right now is nanoparticles. Silk materials for applications in healthcare and medicine and as textiles have been utilized by humans for centuries, like going back to BC times. And so the idea, though, of these natural materials actually being products that could enter the clinical market and assist patients didn't really manifest until the mid to early 2000s. And so our work is really trying to leverage both our new knowledge and improved basic biology and entomology with the needs of clinical applications. So natural materials in clinical settings are really exciting because they're able to degrade once you implant them in the body. Our goals are to really understand what the scale up of this organism looks like and improve the total amount of protein that we are producing, but also start to look at the GMP production processes and how to transition these materials that right now we make on the bench. These organisms are easy to grow. Their life cycle is really short. It's only about a month. We're interested in developing protocols that will fit FDA requirements for production of materials used in healthcare and medicine. I'm really thankful to the collaborations and interactions that we had when I first arrived at UF. We started first working with Paul Shirk at the USDA, and then we're also really thankful to our entomology collaborators, especially those at the Florida Museum of Natural History. I'm particularly thankful for all of my PhD students, specifically Bryce and Lauren. I'm also really thankful to all of our undergraduate students. It's really nice to have that validation that all of the efforts we've been putting in, my students, the undergraduates that are helping to make this work possible, are actually, valid and useful in a commercial potential. I'm also very grateful to Rachel and the entire tech transfer team because I ask many questions throughout our invention disclosure processes, and they're always so willing and helpful, and we would not be here without their support.
The use of what's considered a pest in the United States is a therapeutically relevant bioreactor that drew this invention to our team is really standing out this year and being worthy of the Invention of the Year. So I just want to say thank you to Whitney for telling us about this invention and all of your technologies. It's always a pleasure working with you, and we're always excited to see where you're headed next and what you're going to do with your brilliant ideas.